Why does this happen in Elasticsearch? You index a document. Get by ID works instantly, but your search query still cannot find it. Then someone says, do a refresh. Another says, do a flush. And a third person insists, no, you need a commit. So who is right? In this video, we will make this crystal clear, visually, from the Elasticsearch API all the way down to the OS, syscalls, and disk. Here is the short version. Refresh means make recent writes searchable. It is about search visibility. Flush means reduce recovery risk by persisting translog-backed work into Lucene and rolling the translog generation. It is about durability housekeeping. And commit, in the Lucene sense, means create a durable checkpoint of the index on disk. The common mistake? Thinking refresh equals a full durable commit. It does not. Refresh is visibility. Flush is durability housekeeping. Commit is Lucene's durable checkpoint. Keep these three lanes separate in your mind. Let us start at the application layer. Your app sends an index request over HTTP to Elasticsearch. The coordinating node routes it to the correct primary shard. Inside that shard, the document goes through parsing, mapping, and analysis. Then two things happen in parallel. First, the document is indexed into Lucene's in-memory structures. Think of it like writing notes into a scratch pad that is not yet filed into the cabinet. Second, the operation is appended to the translog, the transaction log. Why both? Because Lucene commits are expensive. The translog acts as a write-ahead log. If the node crashes between commits, Elasticsearch replays the translog to recover operations that Lucene had not yet durably committed. The translog is your safety net between commits. Now the first key concept, refresh. Elasticsearch is near real-time, or NRT, not strictly real-time. A refresh opens a new searcher on recently written Lucene segments, making those documents visible to search queries. Think of it like a library that shelves new books every minute. The books arrive at the desk immediately, but readers browsing the shelves cannot find them until the librarian files them. That filing step is the refresh. Here is the critical point. Refresh is about search visibility, not durability. Your data may already be acknowledged and tracked by the translog, but a search will not see it until a refresh happens. Let me show you the timeline. At time 0, you index a document. A get by ID works instantly. That is the real-time get path. But a search query at 200 milliseconds? It returns nothing. Then, 1 second later, the periodic refresh fires, and now the search finds it. By default, Elasticsearch refreshes about every 1 second, but only for indices that have received search requests recently. This is called search idle behavior. In Elastic Cloud Serverless, the default refresh interval is 5 seconds. And calling refresh explicitly, that is synchronous and resource-intensive, avoided in hot paths. Now let us demystify flush. Flush is not about making your documents searchable. That is refresh's job. Flush is about making sure operations tracked only in the translog are also permanently stored in the Lucene index, and then rolling the translog generation. Think of it like a restaurant kitchen. Orders come in and are written on paper tickets. That is the translog. The kitchen prepares each dish. Periodically, the manager archives the completed tickets and starts a fresh pad. That archiving step is the flush. Here is what happens during a flush. Lucene performs durable persistence. The commit point is updated. Then the translog generation rolls forward from translog 1 to translog 2. Old generations become eligible for cleanup. On restart, Elasticsearch replays unflushed operations from the translog. If you flush more often, replay is smaller, but flush itself is expensive. That is why Elasticsearch auto-flushes using internal heuristics. The official docs explicitly say, users rarely need to call flush manually. Under the hood, Lucene has the concept of a commit point. A Lucene commit creates a durable point-in-time snapshot of the index on disk. Elasticsearch's flush operation is tightly related to this durability process. Refresh, on the other hand, is the cheaper visibility mechanism used for near real-time search. Think of two switches on a control panel. One switch, refresh, opens a new searcher, visibility. The other switch, flush/commit path, triggers fsync and updates the commit point. Durability. If you mix these terms casually in ops discussions, people will make the wrong trade-offs, especially during bulk ingestion and incident response. Know the difference. Use the right term. Now let us descend the stack, from Elasticsearch all the way to hardware. At the application layer, Elasticsearch and Lucene use CPU for parsing, analysis, tokenization, posting list construction, compression, and segment merges. JVM heap holds in-memory data structures and request processing buffers. The OS page cache, and this is critical, is heavily used for file-backed I/O and search performance. Think of it like a filing cabinet with a fast desk in front. The desk is the page cache. Frequently accessed files sit on the desk. Rarely accessed ones require pulling from the cabinet. That is a disk read. At the kernel layer, writes and reads go through the file system and block layer. Syscalls like write, fsync, pred, and map drive the I/O. At the hardware layer, SSD and NVMe latency and throughput determine how painful frequent small writes, fsyncs, and merges become. More IOPS helps random I/O. Higher throughput helps large merge and scan workloads. Here is the cost breakdown. Refresh cost is mostly CPU, memory pressure, and segment churn, which leads to merge overhead later. Flush and commit cost is mostly disk durability overhead, the sync pressure, and merge cost. That can become the real hidden monster running in the background. So is Elasticsearch CPU heavy, RAM heavy, or disk heavy? The answer, it depends on the workload. For indexing heavy workloads, CPU is consumed by analyzers, tokenization, and merge bookkeeping. Disk is consumed by segment writes, translog fsyncs, and merges. RAM matters for heap, OS cache, and buffering. For search-heavy workloads, CPU handles query parsing, scoring, and aggregations. RAM and page cache are critical for hot segments and doc values. Disk becomes the bottleneck when cache misses occur. Now specifically for refresh and flush. Frequent refresh increases CPU load and segment churn. Frequent flush increases durability work and disk sync pressure. Bad tuning of either can reduce throughput dramatically. The worst pattern? Bulk indexing with refresh equals true on every request. You pay the cost now with tiny segments, during search with more segments to scan, and again later during merges. Let us look at real-world patterns and the tricks teams learn the hard way. Pattern 1. Your app writes then immediately searches. Do not force explicit refresh on every write. Instead, use refresh equals wait underscore for only when synchronous visibility is truly needed. Better still, decouple your write and read paths. Pattern 2. Bulk backfill or reindex. Temporarily increase the refresh interval or disable refresh entirely during the controlled bulk load, then restore it. Expect merge activity after ingestion completes. Pattern 3. Incident response. Search is not seeing fresh documents. Before you panic, check the refresh first. Was the write acknowledged? Is the search hitting the right index or alias? Has a refresh actually happened? Are you confusing get by ID real-time behavior with search visibility? Now the optimization tricks. Tune refresh interval based on your product SLA. If 10 seconds is acceptable during ingestion windows, use it. Watch merge pressure, not just indexing throughput. And always size hardware for your dominant path. NVMe for ingestion, RAM plus page cache for search, CPU for analyzers and aggregations. Let us lock it in. Refresh means searchable. It opens a new searcher so your search queries can find recently indexed documents. Flush means translog housekeeping. It persists work into Lucene and rolls the translog generation. Commit is Lucene's durable checkpoint on disk. The real performance story lives across CPU, RAM, page cache, kernel, and disk. Every layer matters. And the biggest production mistake? Forcing visibility too aggressively and accidentally creating tiny segment merge storms that crush your cluster. Refresh is not flush. Flush is not commit. Understand the layers. Tune the right